Okay, then let's get back to the lecture. So now we are going to go into the very interesting part, primordial nucleosynthesis. Why is it here? Is that right? That's right, right? CMB we finished, right? Okay, so primordial nucleosynthesis. Okay. Oh, hi Kiki. Good, you made it. Oh, you missed that I was on TV today. My left hand was on TV. You missed that. You can watch that on the YouTube later. My very beautiful left hand was on TV. TV news about research. Anyway, so Big Bang primordial nuclear synthesis. So this is a triumph of the Big Bang theory. And then this is the reason many people believe there was a Big Bang. So, so this is a theory about Big Bang nucleosynthesis. This is basically this is alpha beta gamma paper by then George Gamow. And then he did this calculation only on the table. You know, this is theoretical calculation. And then in the end, he predicted the abundance of these elements after the Big Bang on the table with a paper. And then that almost perfectly agree with what we observe today. So this is a triumph, isn't it? Isn't it beautiful that you sit down and you calculate, oh, this much helium, this much hydrogen, this much lithium, you calculate, and then what we observe with large telescope today agree with them. That's cool, right? So that's why we call it a triumph of the Big Bang theory. Maybe you have heard that also that first 1,000 seconds, that most of the elements, most of the light elements in the universe was shaped only in 1,000 seconds at the beginning of the universe. That's Big Bang nucleosynthesis. That's what we're going to review today. Okay, so let's get started. So we learned that temperature of the cosmic microwave background, CMB, also scale with 1 plus z. Okay, so if we go to higher redshift by rewinding the clock, that means larger z, and temperature goes up, right? And then when it goes, say, redshift of 1,000 or several thousand, the temperature is going to be also several thousand, right? Okay, maybe I can ask a quiz. When redshift is 1,000, what's the temperature of the CMB? Okay, CMB now is 2.7 Kelvin, right? And there we put, okay, for simplicity, let's say redshift is 999. Do you like that? So 1 plus z is going to be 1,000. Okay, what's the temperature, original temperature of the CMB or universe? Okay, this is 2.7. Okay, so yes, 2,700, right? Good. 2.7 times 1,000, so 2,700. So with thousands of degrees, when elements are at 1,000 degrees, what happens? Bodwin, what happens if elements are heated to 1,000, several thousand degrees?
Collide with fusion?
Yes, fusion, right? Yeah, fusion is going to happen. So it happened in a. But so this is like the nuclear fusion that Bodwin likes, but it's different that at this time it's more radiation dominated. So nowadays, for example, our nuclear plant or the sun's core is matter dominated, right? But then in the universe, it was radiation dominated. Okay, so let's look at this nuclear fusion. Okay. So in thermal equilibrium, this thermal equilibrium follows this Boltzmann distribution. Okay. So in the early universe, between neutron and proton, there was this kind of reaction was going on. Proton becomes neutron, with proton plus electron is going to be neutron and neutrino, electron neutrino, and then it goes back. And also proton and anti-electron neutrino becomes neutron and then electron. So this kind of reaction was going back and forth in equilibrium. The ratio between neutron and a proton follows the Boltzmann distribution, which is something like this. And then what's important is here, temperature here. So in this equation in temperature, so the temperature decides the ratio between neutron and then proton. Okay. Then, okay, so that was the situation in the early hot Big Bang. And then the universe is, okay. Then this reaction rate can be written something like this. So this reaction rate, V, is temperature to the inverse -5 per second. This, we don't do it in this class, but if you're interested, if you learn that a weak nuclear force, then they can derive this -5. Okay, and then in the early universe, we already saw this temperature scale was 1 plus Z, and then curvature, we just think it's very small. Actually, it's very small in the early universe because it's radiation dominated. I keep saying the early universe is radiation dominated. It's a difference between -4 and -3. So you remember that I said the photon density scale with scale factor -4, right? But then matter density scale was -3, right? So when R is very small, -4 wins, right? So photon density in the early universe is much higher than the matter density. So that means, that's what I mean by the early universe is photon dominated. Almost all the energy is in photon, radiation, because it's -4. Because photons wavelengths, it gets also smaller, higher energy, right? So that's why. In the radiation dominated universe, scale factor scale with T square root. This is what I skipped a few weeks ago. If you're interested, we can come back to this. This is one of the exercises a few weeks ago, but I remember I skipped. If you want to do this, just let me know. Or maybe when we have what time is it now? Is it 1 p.m.? We still have 4 hours of 4 hours. Then we have enough time to do this exercise, so we can do it. But okay, maybe seriously, when we have extra time, just remind me to come back to this. Because this is important. But for now, we take it. It's a square root photon-dominated universe. Then if you modify this to T, then T proportional to R squared, right? Then you can write it with 1 plus z to the minus 2, and then that's also through that you can write it in t minus 2, because r is related to 1 plus z here, right? So you put it in here, 1 plus z, then it's reverse, and then this is going to be t minus 2. Okay, so anyway, t, this is the age of the universe, time from the beginning of the universe. It's scale with t minus 2. Okay, minus 2. Okay, minus 2. Okay. Then reaction time scale is something like 1 over b. It's b is somewhere at b is here, right? b is t to the minus 5, right? Okay, that's reaction rate. And the inverse of reaction rate is reaction time scale. So this is t to the minus 5. And then now, this t is temperature. And if we put age of the universe, then we put this minus 2 here. So it's going to t to the 2.5, right? So this small t is the age of the universe, time from the beginning, start of the Big Bang. Okay, and then this reaction time scale is going to be t to the 2.5. So it's very, very quickly becomes large, right? T to the power of 2.5. So here, right, that if universe gets older as the time goes by, reaction time scale gets larger. And then when the reaction time scale gets too large, then that reaction cannot happen anymore, right? So to be more precise, when this age of the universe becomes time scale, reaction time scale, or reaction time scale becomes larger than the age of the universe, then there's no more reaction happen. No more reaction happens. Then at that moment, remember this, I was saying that this reaction was this reaction was going back and forth, right? Proton to neutron, neutron to proton. This was going exchanging, right? But when that moment, this is not going to happen anymore. So the ratio of proton to neutron is going to be freeze at that moment. So this is a concept of the freeze out here. So when the reaction time scale gets bigger than the age of the universe here, then the ratio of neutron to proton is going to be fixed. There's no more reaction between this. And then that's called freeze out. So this freeze out is the most important concept of the Big Bang nuclear synthesis theory. So please try to understand the idea of this freeze out today. Okay, this is most important topic today. Okay? After students' presentation. This is most important. Okay, so let's calculate. Okay, when does that happen? So when does the age of the universe become the same as the reaction time scale? So we just put this equal, right? So this is reaction time scale. And this is the age of the universe equals reaction time scale. And then you can solve this for the temperature large T. And then the answer is temperature is 10 to the 10.142 Kelvin. That's a very high temperature, no? 10 to the 10 Kelvin. How do we read it? 1 billion, billion is 90, right? So 10 billion degree or something like that. That's very high temperature. And then in terms of time, it's about 1 second. So at 1 second at the beginning of the universe, this ratio fixed between neutron and a proton. What's the ratio? Neutron to proton ratio, you put this number in, 10 to the 10.142 here. This is Boltzmann equation, right? If you put the Boltzmann equation, it becomes 0.34. That's the ratio. And actually, this is very simple calculation. So in reality, if you want to calculate more accurately, this transition takes some time. It doesn't freeze out instantly, right? There's some time scale to freeze out, right? So if you consider all these details, you get 107, 1/7 is the proton to neutron ratio. It's not too much different. And then as I said, if you observe the neutron to proton ratio of the whole universe, it's this value. We observe it. So this calculation came from the theory on the table, right? But then this derived value, 1/7, it exactly matches the observation. That's cool, right? This George Gamow didn't know the ratio, because the ratio was measured much later. But in 1934, he predicted this ratio. And then years later, people observed the ratio, and he was correct. That's cool, right? Yeah, maybe I should predict something, and then so okay. Oh. Yes, not just left hand side. Yeah, okay. And then this continue, okay? Now what happens? So neutrino, okay. And then in the next 1,000 seconds. So we're talking about this neutron-proton reaction, right? And when this freezes out, when temperature goes down a little bit, next one happens. This neutrons decay, and then that creates a deuterium, and then deuterium to helium, deuterium to then helium here, and then helium, lithium, and then as the reaction goes through, the universe is going to create more and more and more heavier elements. And then at each steps here, there's a freeze out. So this one, in 1 second, freeze out, right? And the universe keep expanding even after that. And after that, this neutron decay is going to happen, right? And neutron decay is going to continue 100 seconds, but the neutron decays also freeze out after 100 seconds. We don't go to details because this reaction is going to be more and more complicated, but it's the idea is the same. So when the universe expands, then the reaction time scale becomes longer than the age of the universe. So this one particular reaction cannot happen anymore. So that's freeze out. So first this freeze out, next this freeze out, and next this freeze out. And so that happens. The freeze out happens one by one. And then at each step, this freeze out is going to fix the ratio of these elements, and that decided the ratio of the elements in our universe. Okay, then this is what you get from the calculation, right? So this is the fraction of elements in terms of mass as a function of the age of the universe or time from the Big Bang. And then, let's look at helium, right? Helium is this green, right? Helium is created, increase, and then freeze out here, right? At this point, the universe is too big, reaction time scale is too long, so the abundance of helium is freezed. It's the same, right? And then that happens to all other elements. So for example, this one, this increase, and then freeze out. And then this, and then lithium too. Lithium increases and then freeze out here. Okay. And then beryllium too, right? The beryllium increase, reaction happens, and then freeze out and fix. So that's how the elements are created in the early universe. So the ratio so that's why some people say, was it like a Stephen Hawking, like our element first 3 minutes that shaped our universe? It's talking about this. Okay, now let's compare with observation. So the George Gamow, through this Big Bang theory, nuclear synthesis theory, predicted abundance of elements, right? Then now we compare with the observation. Okay, so here it's the same. This is the number abundance relative to hydrogen, and then for example, deuterium. This red curve is a theoretical prediction from the Big Bang theory. And then deuterium is predicted like this, lithium is predicted like this. And then this actually, the number abundance, number ratio depends on the omega baryon. So how much baryons are available in the universe, it depends on this. So we need this value, but then this value is precisely measured from cosmic microwave background, which I will tell you how to measure from the cosmic microwave background, but we can measure this very precisely. So we just take this value. And then deuterium is a perfect agreement. So this observation is in this blue area. And then theoretical prediction is this red curve. So this George Gamow's, paper prediction, it perfectly agree with observation here. And then lithium has it's mostly, agree with well, but then lithium, it's more complicated because lithium is created or destroyed in stars. So lithium abundance can change after the Big Bang. So it's more difficult to match compare with a theory. But anyway, most of the elements agree with this Big Bang theory, so that's why it's called the triumph of the theory. Okay, this little difference of the lithium is called lithium problem, and then it's an active debate of the topic. There are a lot of researchers still trying to figure out why there's a difference in lithium. Oh, it's created in stars, it's destroyed, and blah blah blah. So, okay. And then there's a little bit side story. Neutrino, at the time of the Big Bang, it's also subject to freeze out. So for neutrino, we have this kind of reaction what's going on at the time of the Big Bang. This is electron and positron goes to electron neutrino and anti-electron neutrino. So this reaction was going on. But then in the same way, when time is the age of the universe was 0.18 seconds, this reaction froze out. Then this becomes this amount of neutrino, it freezes out, and then this neutrino becomes cosmic neutrino background. So when in the future, so now we can measure the cosmic microwave background, right? But we cannot measure cosmic neutrino background because our neutrino detectors are not so sensitive. However, in the very far future, maybe 5,000 years from now, if we can build a very sensitive neutrino detector, then we may be able to measure cosmic neutrino background. It is there, according to the Big Bang theory. Okay, then there will be a side story here. So this guy, George Gamow, was, it seems a very unique, he had a very unique personality. You can imagine from the alpha, beta, gamma theory, right? So he wrote a lot of popular science books. So, and then these are poems that he wrote. So here, Twinkle, Twinkle, Quasi-Star. Quasi-Star is a quasar. Biggest puzzle from afar, how unlike the other ones, brighter than a billion suns. Twinkle, twinkle, Quasi-Star, how I wonder what you are. So, this is, the song, right? And then quasar at his time was a mystery. Nowadays, we know quasar is, some emission from supermassive black holes with I don't know, million or 2 billion solar masses. But at that time, people didn't know about it, so people thought it looks like a star, but it looks weird with the redshift, so what's going on? So he wrote some poet like this. Then the next one is, it took less than an hour to make the atoms, a few 100 million years to make the stars and the planets, but 5 billion years to make man. Yeah, I mean, as you saw it, like in most light elements in the universe was created in 1,000 seconds at the beginning of the universe, but then it took million years to make the stars and planets, and then billion years to make people. So that's what he wrote here, that's true. And then these are one of the popular books, popular science books written by George Gamow. So this Mr. Tompkins. So in this series of books, Mr. Tompkins goes to some part of the universe, and then he experienced a strange the universe. For example, he goes to I thought this was, I don't know, this may be neutron star, and then the gravity is too strong, he cannot move anywhere at all. So that's interesting story, right? So that's interesting book. Maybe if you have time, you can take a look at it. These kind of books are in our library, so you can take a look. Okay, so that's the end of this chapter. Any question? Okay, then maybe we have a 10 minutes break, and then after break I can talk about introduction of inflation, maybe. Okay. Shall we have a 10 minutes break? Yeah.